Neyman-Pearson's test of acceptance, misinterpretations. This third and last presentation in the series adds further information about theoretical and philosophical misinterpretations, which are important because may lead to pseudoscientific conclusions. Now, as we have already discussed, Neyman-Pearson's decision theory is a different approach to testing research data. It is more technical and deductive, but also requires good knowledge of the populations of reference and the use of fixed decision parameters. It is a theory which is most suited to repeated sampling projects, such as quality control and large-scale diagnostics. There is, of course, the potential for misinterpreting the test even in these situations, and this is therefore the focus of this presentation. Now, again, Neyman-Pearson's tests refer to known or assumed population effect sizes, which inform the correct hypothesis. Therefore, these hypotheses are always true empirically or theoretically, and they are not put to test. What is tested is the research data against this hypothesis, not the hypothesis itself. Therefore, using this theory as if it were testing hypothesis is a pseudoscientific misinterpretation, as this is not actually what the test does. And so it is also a misinterpretation talking about proving or disproving hypothesis, or talking about the truth or falsity of the hypothesis. And so it is to conclude that the p-value of your research is the probability of the main hypothesis, and its inverse 1 minus p is the probability of the alternative hypothesis. Now, misinterpretations regarding the main hypothesis. The main hypothesis is the only hypothesis used for the test, but this doesn't mean that it is just a null hypothesis. Believing so and thus ignoring what the alternative hypothesis offers to the test is a pseudoscientific misinterpretation. For example, the alpha level aims to control the risk of making a type 1 error in the long run. It is not a threshold of evidence against the main hypothesis. So alpha is not a local error probability that can be adjusted after calculating the p-value. And equally, the p-value is not the probability of making a type 1 error when accepting the alternative hypothesis. Also, the alpha level cuts off a part of the effect sizes which will be taken as being explained by the main hypothesis. This implies that the main hypothesis is not simply a null hypothesis equal to 0, but includes a range of effect sizes deemed to be of little interest under the alternative hypothesis. These effect sizes are ultimately determined by this alternative hypothesis. And a final consideration is that given enough power, the main hypothesis can be accepted as an explanation for the data. Again, the main hypothesis is not a dummy null hypothesis, but represents a real distribution of effect sizes in the population. Misinterpretations linked to the alternative hypothesis. Now, the alternative hypothesis is not just simply a negation of the main hypothesis, as it happened, or a negation of a null hypothesis. The alternative hypothesis provides valuable information to the test, namely about the population effect size, type 2 error, and therefore about power. Now, the alternative hypothesis actually determines where the minimum effect size threshold sits. Thus, it determines which effect sizes will be considered as important and which will be considered irrelevant under the alternative hypothesis. Or said otherwise, the minimum effect size is that effect size that corresponds to a local p-value similar to the alpha value, approximately so, after considering, sampling variations. As it happened with alpha, the beta level aims to control another risk, in this case the risk of making a type 2 error in the long run. So beta is not a local error either, and it cannot be adjusted a posteriori after collecting the data. And again, just to repeat what we said before, this is the interesting thing. If the information provided by the alternative hypothesis is not taken into account when setting the test, then by default you are doing Fisher's test of significance, even if you name it after Neyman and Pearson. Now regarding power, the power of the test has two purposes. One is to increase the probability of capturing effect sizes that are due to the alternative hypothesis, but also to be able to say something about the main hypothesis otherwise. That is, accepting the alternative hypothesis is possible even if power is low, because the effect size has effectively been captured. So it would be pseudoscientific not to accept the alternative hypothesis when power is low. However, in the same situation, it would be risky to set the main hypothesis, because the results may still be due to the alternative hypothesis. So it would be pseudoscientific to accept the main hypothesis when power is low. And now regarding decision making. Now, Neyman-Pearson's is a decision theory, not an evidential one. Thus, it is a pseudoscientific misinterpretation to use the p-value as evidence against the main hypothesis, as we do with tests of significance. It is an even worse misinterpretation to suggest that the probability of making a type 1 error now matches the p-value, so the so-called robbing alphas. And again, just to repeat what I have said before, it is a pseudoscientific misinterpretation to conclude only about the alternative hypothesis, but to treat all results under the main hypothesis inconclusive, even when power is adequate. Again, Neyman-Pearson's is not a test of significance, but a decision theory, with the particularity that power can be controlled a priori precisely in order to make a decision regarding the two hypotheses used for the test. And two final considerations. One is about meta-analysis. Meta-analysis doesn't suit Neyman-Pearson's approach. The goal of the meta-analysis is to estimate the unknown population effect sizes better by way of aggregating related studies. So, Neyman-Pearson's approach is already based on known population effect sizes, and meta-analysis is therefore unnecessary. But using it may lead to the misinterpretation that parameters inferred from samples are more reliable than known population parameters. And a second consideration is about replication. It's a misinterpretation to take a contradictory result provided by a follow-up study as evidence of replication failure. Neyman-Pearson theory assumes long-run repeated sampling, so just the one replication is not enough to contradict a previous result. Actually, replication studies should match the power selected for the test, so just keep the same power throughout replications, so that we can't see, for example, an 80-20 split between supporting and contradicting replications when power is set to 80%. And in this situation, a minimum of 4 replications, not just the one, but a minimum of 4 replications will be needed for ascertaining that such a split is kept. More replications so if you want to be sure that the split is kept in the long run. And with this, we finish the presentation and the series on Neyman-Pearson's test of acceptance.